Folks, welcome to Rocket Science 101. Today we're going to derive the equation for gravitational potential energy in space. Let's check it out. When we think about potential energy, we usually think about an object close to the surface of the Earth. An object like maybe this ball. This ball has a mass m and it's at a height h from the ground. Well, then its potential energy, PE, is defined as mgh, where m is the mass of the ball, g is the gravitational acceleration of the Earth, 9.8, and h is the height of the ball from the ground. Now, the pro of this equation is that it's remarkably simple. It basically tells you how much energy can be converted from here into other types of energy, like kinetic energy or other types of energy. But this formula has a con. It only works for distances close to the surface of the Earth. If you're in space, for example, you cannot apply this formula. So what can you apply? Well, that's exactly what we're going to derive. We're going to derive the gravitational potential energy formula right now. Okay, so what is gravitational potential energy? Gravitational potential energy is described as such. Imagine you have the sun. The sun is shining, bright, and happy, and we have the Earth. So here's the Earth. I want to find the gravitational potential energy of the Earth in its orbit around the sun. How do I do that? Well, here's what you have to do. You have to pretend like you're bringing the Earth from some infinitely far away radius. So let r sub I, the initial radius, be infinity. You're bringing the Earth from infinity to the current radius. So that's going to be r sub f is equal to r. Okay, so there's some external force pushing the Earth from a radius of infinity to a radius of r, and that external force, the work done by that external force, is going to be the potential energy. That is the gravitational potential energy's definition. So let's go ahead and formally define it right here. So the gravitational potential energy is defined as such. It is the work done by an external force, to bring an object from a radius, from an initial radius of infinity to a final radius of r. Okay, that is the definition, the formal definition of gravitational potential energy. Now let's convert this English definition into a mathematical definition. First thing you want to do is look at work. What is work? Well, we know work is just Fd, right? Where F is force and D is distance. If you want a more visual description, of course, you can graph what work looks like. It is the area under the curve FD. So if you have a constant force, for example, 2 newtons of force acting on some block for 5 meters would be 10 joules of work. And of course, work is just the area under this graph, the area under the force distance graph. Okay, so here's the caveat. The caveat here is our force is not constant. Why is our force not constant? Well, gravity is one of the most famous forces that is not constant. Remember that Newton told us that Fg is equal to gm1 m2 over r squared. That means the gravitational force F sub g varies inversely with the square of the radius. And so you can see that gravity is not a constant force. That's why we can't just use Fd, force times distance, to find the potential energy in space. Instead, we have to use calculus. So let's go ahead and do that. I'm going to use my brown chalk right here, and we're going to use integration to integrate from r is infinity. So this right here is r equals infinity, r initial equals infinity, to r final is equal to r. So we're basically integrating over this region right here. We're trying to find the area under this region. And of course, Newton times meters, Newton meters, joules, that's going to be our work or potential energy. Okay, let's do it. How are we going to do that? Well, let me use my red chalk or my purple chalk in this case. So what we're going to do is use the integral from r is infinity to r. So r sub f is equal to r, and it starts from an initial radius of infinity. Okay, so we're bringing it from here to here. You don't start from here to here. You start from here and you're bringing the object to a radius of r. Okay, and what is our integrand going to be? Our integrand is going to be f dr. So let's write that down. Let's write down f dr. Okay, so now we can go ahead and expand here. What are we going to expand to? Well, we know what f is, right? So we're going to have infinity to r. Instead of writing f, I can just write this equation right here. G big M small m over r squared. And then I can write dr on the outside. And now notice what I have right here. Right here, you can see that this whole thing on the numerator is a constant. So I'm going to pull that out right here. So since that's a constant, we can write this is equal to G big M small m. And then we have our integral from infinity to r. And here we have on the inside, we have r to the negative second power, and we're integrating with respect to dr. And so what is this going to give us? Well, we're going to end up with minus g, let's use a better part, minus g big M small m over r. Okay, that, ladies and gentlemen, is the gravitational potential energy of an object in any location in space. And so what does this mean? How can we contextualize it? Well, let me go ahead and draw out what this means for you, so you have an idea of what we just derived. So what this formula is telling us is how much potential energy an object has in space. So let's say I have the Earth right here. Here's my planet Earth, the big blue marble. Here's the Earth. And let's say I have some rocket, okay? I'm going to have my rocket out here in space on some kind of a trajectory, a circular trajectory around the Earth. Here's my rocket. And my rocket is maybe accelerating, maybe it's burning some fuel, or maybe it's trying to get into a high or lower Earth orbit. So here's my rocket burning some fuel, okay? Now here's the thing. What's the potential energy of my rocket in its low Earth orbit? That's the question we're posing here. What is the potential energy of my rocket in its orbit? Well, to answer that question, we literally use the formula I just derived, right? To find the potential energy of our rocket, all we have to do is use this formula. Minus G big M small m over r, where r is simply the distance, the radius really, between my rocket and the Earth. And that, ladies and gentlemen, is how you derive the gravitational potential energy formula for outer space. Thanks for watching this video. We'll check you out next time.